now to the topic of my talk, and this will be a kind of dipole talk with two topics, and let's say perhaps I will start just the opposite as it is written. So first I will give you a kind of news flash about non-locality of a single photon, and then I will move to physics and metaphysics of Wigner's friends, and the question, really this is a question of whether we can have measurement results in case of pre-measurements. I hope that it will, okay. So let's say, as I told you, something that is as part 2 in the title will be my part 1, but it is not as big a paradox as those in quantum mechanics. And so this will be more or less, I will tell you something about our paper wave particle complementarity detecting violation of local realism with photon number resolving weak homodyne measurements. And this is my team and in ICTQT, and ICTQT, this is a new center formed in Gdańsk, and the idea is to, let's say, build on the experience of ICOKI and build something like an ICOKI in Poland. And we received money from the Foundation of Polish Science, which is an NGO, totally non-governmental organization, and the origin of the money is the EU budget. And let's say, so the experiments that I'm going to talk about, as I told you, will cover the situations where we have weak homodyning and photon number resolution. So I will be talking mainly about experiment of Tan-Walls called 1991, the Gedanken experiment by them. And then I will say a word about Grangier, Potasek-Jörke, even earlier Gedanken experiment. Okay, so this Tan-Walls called experiment was kind of marketed as something that shows what they call non-locality of a single photon. And the idea of the experiment was to have a single atom which impinges on 50-50 beam splitter, and then let's say it is in a superposition of being in beam 1 and B2, and then it hits the state hits two other 50-50 beam splitters. This is important here that they are 50-50. Where a weak homodyne measurement is made. That means that there's a local oscillator and the alpha is not too big. And finally, let's say the idea was to measure intensities according to them, but really this can be, as you know, that let's say intensity in quantum optics is proportional to photon number, so there are two detectors that were detecting the photon numbers. Okay, and the Tan-Walls and Collett, they plugged the correlation functions that they derived for such a system into Bell inequalities, and let's say, the word Bell inequality is a misnomer, into something what they believed is a Bell inequality. And they show the violation, and therefore their thesis that you can see in such an experiment a violation of local realism, or as they call it, non-locality. And what is very important, let's say the local settings were defined by the phases of the local oscillators. Okay, so the amplitudes of the local oscillators were constant, and also the reflectivity and transmittivity of the beam splitters were constant, and that was, according to them, let's say, led to, let's say, proper violations of Bell inequalities. Okay, and as I'm still with the slide, I will just have to tell you that the Grangier-Potasek-Jörke experiment has exactly the same configuration on the measurement side, but instead of a single photon, we had a down conversion crystal and two beams entering here, and they also claimed that there is a violation of local realism, and the kind of curse is that they were using the same inequality, which is not a Bell inequality. Why I'm talking about it? Because let's say the time is right to have a conclusive statements about experiments like that, because it turns out that now we have photon number resolving transition edge sensors, which were used by Wormsley and his group in several papers, and they allow realization of those emblematic experiments. And so I remind you that the first is excitation of a pair of spatial modes by a single photon, and the second is two spatial modes in weakly squeezed vacuum state involving, and let's say everything is involved in both cases, involved constant local oscillator strength, and there are just the measurement settings are defined by the phases of the local oscillators, as are right here. Okay, and what we show in this paper, and also in a, let's say, series of papers that accompanied, is that experiment A in the configuration of Tan-Waltz collet has an exact local hidden variable model, absolutely exact. And in case of experiment B, in this configuration with constant local oscillator strengths and just phases defining the measurement settings, claims of non-classicality are unfounded. And finally, we also give let's say a way to show that there is a violation of local realism, but you have to substantially have a different look at the experiment and substantially different operational situation. And the situation is even more grave in case of those experiments, because, for example, in one of the classic textbooks about quantum optics, Milburn and Walls, on page 264, one can read some of the most striking features of non-locality in quantum mechanics may be demonstrated using phase-sensitive measurements on the field produced by a single photon. These effects may not be explained classically using a particle wave or hidden variable theory involving local causality. So this statement is plainly wrong, because we have a hidden variable theory for this experiment. And also there is a book which is classified by Springer as a textbook, the story of light, science, and so on. So. And this is based on let's say there is a whole chapter about this single photon effects, and this chapter is based on paper which is in New Journal of Physics 2008, and in archive it can be found in such a number. And the thing is that we have, on the way of analyzing all that, found that let's say the predictions of this paper are completely wrong. So, for example, the whole chapter in here is totally misleading. Okay, so I will go very briefly through this. So I will concentrate only on the Tan-Waltz collet situation. So just look that after the beams, initial 50-50 beam splitters, one has the following state if you look at the situation from the point of view of the modes occupation numbers. Okay, and of course this resembles a maximal entangled state by let's say, which is used in Bell's inequalities, and that's why it is let's say a lot of people seeing something like that, they immediately think that there must be a violation of Bell inequalities, and so if they get it, they are very happy. And the quantum predictions for this precise for all possible events. Okay, so this is number of let's say all local detectors are C or D. Okay, so and Alice is number 1 observer and Bob is number 2 observer. Okay, so it turns out that the quantum predictions have a very nice characteristics. Okay, they depend only on the difference of the local phases. And then just look, there is some amplitude, but look, whenever there's an equal number of photons detected on Alice's side, this is 0, so there is no phase dependence. Okay, so there are phase dependent situations only when there are different numbers of photons in C detectors and D detectors on both sides. Okay, and this is, let's say, if you look at this, so you have quite a lot of events which are, let's say, non-interferometric events, as we were technically calling it ourselves, and some events are interferometric. Okay, and let's say what we did is we adapted a model by Janok Lashun from 1999. As a matter of fact, it was first published in my paper with Ertz, Paul Kwiat, and Janok concerning Franson interferometry. And this model of Larson emulates quantum predictions for 2-qubit singlet. But, of course, there must be an efficiency threshold, so a threshold of 2 over pi. Okay? And otherwise, it's 100% visibility, whatever you like. Okay? And so our model is a convex combination of submodels, which are chosen with let's say, specific probability. Just a glance at the Janok model. So on, let's say, Alice's side, we have let's say one local hidden variable. Let's say every photon carries a map, okay, and so let us see that here is a one hidden variable and here is another hidden variable, and as you see, there is a sinusoidal region which tells to Alice detectors show result +1. Okay, so that means to be. Please be delivered in detector C, okay? And on the Bob side, we have a trivial map, okay? So there are just minus and plus results and flat regions. And then if you put those two maps on transparencies and overlap them, then you will see that if you relatively, and what is very important, the local setting is simply shifting horizontally those models, okay, by the value of the local phase, okay, and so when they are shifted, okay, then you'll see that there is an overlap here of plus region, okay, and it's so just the area of this region is, as you know, this is integral of the sinus, and of course it's a sinusoidal function, okay. And that's the end of this, let's say, that's how the model works. But the necessary condition of the model is to have this non-detection events. And then we apply, let's say, we link those events with different K and Ls. These are two different photon numbers at Alice's side and two different photon numbers at our side, with events in which Alice does not see any photon, and Bob sees the same numbers, and other way around. Bob does not see any photon, and Alice sees KL. And we build for each such situation a Jan-Oke model. And for other situations where there is no phases, we just give trivial models. That means that, let's say, there is no dependence on the local phase, so simply, let's say, the models are deterministic, okay? And it turns out that you can construct such models for alpha, which is less than 0.87, and Ktan-Walls and Colette predicted violations of local realism for alpha squared less than square root of 2 minus 1. So as you see, we have even too higher power range, and of course those violations are not true. Okay, and so is there a way out? And really, we were studying hard this idea. Who gave really let's say, a correct, let's say, version of the experiment, but for a different situation, because he was not considering single photon. And even our latest analysis is showing that he was considering, let's say, that the initial state, which enters this 50-50 beam splitters from the side of this, where the single photon was entering in my picture, that this is a superposition of vacuum and a single photon state. Okay, so and it turns out that if you have 8% of vacuum, then basically Hardy's reasoning gives violations which are of the order of 1 millionth, of 1 million. So they are experimentally inaccessible. Of course, there is a region of strong violation, but we took from Hardy the idea to have one events primed in our case, which are just very highly specific count event. Okay, that means a single photon is detected in mode D, and no photon is detected in mode C. Okay, so this is a collapse to just there's no degeneracy. Okay, it's from the point of view of quantum theory, it's a collapse to certain eigenstate. Okay, and in such a case we have the beam splitter inside, and there is an optimized transmittivity opposite, and the local oscillator field is on, and we call it on settings. And then there are events of the other kind, in which we have a single photon in D1. The local oscillator is off, and that's why we call it off settings. And even there is no beam splitter. Okay, so that's if you remember the drawing. Okay, let's say if the local oscillator is off and there is no beam splitter, so this poor single photon, if it hits on the D detector, it will never fit sorry, I think it's not working. It would never hit the C detector. Okay, and of course events B and B prime play the same role for both. And with this, you can show violations of local relation, and something that to puzzle you, okay? And let's say we have stumbled. First, we thought it's a numerical accident, but now we can claim that it's a fact. The necessary condition for optimal settings, that means that which give in such a scenario the optimal violations of Clauser-Horn inequality, satisfy this very strange condition which we don't understand. Okay, that the power of the local oscillator must be equal to the reflectivity of this measurement beam splitter. Initial beam splitter, let's say, is always 50-50. Of course, we consider also the other case, but that's another story. Okay, and we challenge all of you to find, let's say, some lovely, deep, let's say, explanation for that. Okay, and so let's say the summary is the Tan-Walls-Collett experiment, the way it was done, and still I have to say also the way it was done by the Wigner group, because they followed just the blueprint of Tan-Walls-Collett, cannot reveal non-locality of a single photon, as they call it, because there is this model. You have to modify it into on-off situations. And what is very important, also Grangier-Potasek-Yerki experiment, which was involving parametric down conversion and basically 2 photon emissions from it, but homodyne measurements. There is no evidence that it violates a Bell inequality. So this is something about, that's the end of the news flash. And the second topic that I want to touch is physics and metaphysics of Wigner's friends, and subtitle, even performed pre-measurements have no results. Okay? This is a paper by Marcin Markiewicz and me, and it appeared in Physical Review Letters. Fortunately for us, on the 2nd of April 2021, we were relieved to see this date. And why, let's say, the motto of our paper is a statement by Bohr, which I believe we borrowed it, let's say, from Časlav, because Časlav is excellent in quoting Bohr, and we try to quote Bohr rather than Einstein on in the situations which involve, let's say, foundations of quantum physics, because we think he was a little bit closer in understanding all that. When considering those Wigner's friends problem, one has to follow this motto. The ambiguous account of proper quantum phenomena must, in principle, include a description of all relevant features of experimental arrangement. And following this we shall show you that there's something very bad with the concept of Wigner's friends in the way Deutsch has formulated. Let's say the original Wigner's friend is fully okay, but Deutsch's version is pathological. Okay, and our motivations were, of course, papers which brought in the Wigner's friends back to the, let's say, current discussions about foundations of quantum physics, and I think, let's say, the renaissance of this was with the Frauhiger-Renner paper, Quantum Theory Cannot Consistently Describe the Use of Itself. For me, this is a highly provocative title. But really, I was pushed into this after reading this title, which is Experimental Test of Local Observatory Independence, because I never understood this title. And so I started to read about this, and finally I found some understanding. Okay, so the question is about whether the Deutsch type Wigner's friend, whether they form a consistent notion. And of course, all that is linked with something that is called measurement problem. Okay, I put it in inverted commas because for some this is a problem, and for some there is no problem. Okay. And let's say for those who stick entirely to quantum mechanics, there is no problem because quantum mechanics is only probabilistic descriptions. Okay, so the final product of quantum calculations are probabilistic description. Okay, so there is no problem. The only thing is there was an intellectual problem but of course for some this is a real problem if they think that there must be a theory which leads to a definite, let's say, deterministic situations, or which is able to explain why this or not that detector clicked, and then this is still a problem. Okay, and so the measurement problem in the early stages was due to a tension for some, I stress, between unitary evolution and measurement process. The 1930 solution of the measurement in quantum mechanics was the collapse of the state, or with better wording, of the knowledge about the system, update after a measurement. And it was introduced by von Neumann and really clarified by Lüders. And what is very important, Bohr was always claiming that in the measurement situations, one has to take into account interaction with macroscopic instruments. and in a way, this, let's say, for some, it was already giving the kind of satisfying answer. But later, there was a series of work which introduced decoherence as a crucial element of decoherence as a crucial element of understanding of the measurement process, and really, let's say, decoherence simply leads to irreversible situations in which the system is described by includes all the coherences, and it is described by a density matrix with eigenstates of the measured observable being the probabilities of the given measurements. And of course, this similar thing applies to the measurement apparatus, because it is classically correlated with the system after that, and all the coherences are gone. And what is very, very funny in a way, the most beautiful description of decoherence one can find in the book of Bohm, but that was 1 year before he became a Bohmian. And of course, the flag bearer of decoherence problems is Wojtek Żurek, and this is the correct pronunciation of his name. Okay, and perhaps I would just spend 3 seconds on that. Warning: our analysis will be totally within the quantum formalism. Okay, of course, we shall analyze something that goes outside of it, but using only quantum formalism. Okay, so there will be no specific interpretations or something like that. Okay, so let us discuss what is original Wigner's friend. Okay, so we have a system in a superposition, for example, like that, and then a friend measures it and sees either this or that, okay, or rather plus or minus she sees, okay. But a friend is in a sealed lab, and Wigner has no access to this sealed lab. So for Wigner, the whole everything that goes inside of this sealed lab is a superposition of friend with the system. Okay, and then according to what was stated by Wigner originally, Wigner just opens and sees. Okay, this or that, and so Wigner is just checking. The measurement result was sitting there and waiting, but he just checks. Okay, and then came a perversive modification by Deutsch in 1985, in which he allowed Wigner to perform a measurements on Friend's lab in a basis which is effectively complementary to Friend's measurement basis. And I will so to put it short, Deutsch Wigner could check whether Friend and the system are in such an entangled state. Okay. And so this is not the way Wigner envisaged it. And so those papers that I mentioned, they were showing various paradoxes or bell-like situations, and all of them share one thing, which is, from our point of view and from the point of view of quantum measurement theory, which includes decoherence, there's undefined status of measurement by Franz in all those papers. Okay, because we can, if you look at the papers, it looks like, and this is indeed so, that really there is a situation A that there is a situation B in which the friends are performing reversible pre-measurements only. So only this first stage in which they are, or their measuring device are getting correlated, or if you like, entangled with the measured systems. Okay, but of course, from the point of view of measurement theory, let's say the only proper measurement is irreversible, and it involves decoherence. Okay, so we shall analyze those experiments using either hypothesis A or hypothesis B, and we find a surprise that both in the case A, in both cases, sorry, there should be no Deutsch Wigner friend is an internally inconsistent notion. Okay, and so let us derive this inconsistency, and we shall do it in 3 steps. First, we shall apply standard measurement theory.
Marek, sorry, you have around 7 minutes. Okay.
Yes.
Okay.
But I think I have 8 minutes because I started.
Okay, well, 8, yes. Okay. 8 minutes and many slides, I see, but okay. I just want to check that everything's under control.
Yeah.
Okay, good.
Okay, so now I have 7. So step 1, we used standard measurement theory, and if it involves decoherence, of course, Deutsch friend is impossible. Deutsch friend situation, because really what is impossible, it is impossible to measure by Wigner whether the friend and the system are in the entangled state. Okay. Then we give to this situation a second chance. We assume no decoherence in friend's lab, because standard measurement would mean that in friend's case there is a decoherence. Okay. Still, we allow, let's say that friend has a hallucination of an outcome, but we notice the following: that the friend's outcome is erased by Wigner's complementary measurement. If he is capable to make those measurements, which give let's say, as eigen states have the correlated state of friend and the system, then it's impossible for Wigner to tell what was the result of claimed by the friend, because it's erased. Okay, and because of that, we start to claim that the result of friend is a counterfactual. And why counterfactual? Because had Wigner been Wigner's Wigner, he would have just checked, and the result would have been reviewed. Okay, so it's a typical counterfactual situation. And in step 3, we consider counterfactual outcomes. Okay, we consider counterfactual outcomes, and we look at their possible algebra, and we see that it's internally inconsistent. Okay, so let's say I will go through those transparencies very, very quickly. So just look, if let's say if we have a I want to tell you briefly that in the quantum measurement theory, pre-measurement is the correlation of the system with the measuring device, and let's say here I used the device and the friend as a total system. Okay, so we had initial state like that, and then we have a correlated state, and therefore the laboratory of the part of the laboratory of the friend which is not coupled to let's say before there is interaction with the environment goes into such a superposition, which is in fact an entangled situation. If you look at the system and the measurement situations. Okay, but if we have environment additionally, then the whole state in the lab is described by something like this. And then you immediately see that the lab of, let's say, if you trace out the environment, the system of let's say system plus friend and his device are in a mixed state. Okay, and now if super Wigner is to do what Deutsch asks it to do, this experiment will give only random results. I hope that it is absolutely obvious. Okay. Now let us look at the following. That there's also let's say one conclusion from that is that irreversible proper measurements by friends. There's no paradox. There's no there's no Deutsch properties. Okay, and what is even more teasing, a global unitary description by Wigner is wrong if they forget about the environment in French lab. Okay, so now let us move into virtual frames, which are Deutsch frames. Okay, and friends just pre-measure. They just pre-measure. Okay, so the final stage of what is happening in the lab is this. There's no environment, but still they somehow, as it is postulated not by us, they know which was the result. So let's say from the point of view of quantum mechanics, this is a hallucination. Okay, and then super Wigner performs an effectively complementary measurement, as Deutsch would like to him to do it, and after that, let's say super Wigner knows only the result. Let's say he erases all the information about the result obtained by friend. Why? Because let's say the system collapses into the superposition. Okay, or he would have received the result had he been measuring in a basis which is concurrent with the basis of the friend. Okay, and so we move to the final situation. Sorry. Okay, and so now we say, okay, let there be those hallucinations. Okay, let there be those results. Okay, so there is a pre-measurement, but we can somehow associate a result. It may be transitory. It may be erased immediately by super Wigner. Okay, and we show that there is a logical inconsistency in something like that. Okay, and to do this, I hope that I will finish it in 3 minutes. So, Antonio, please don't worry. Okay. So we take let's say if it's always better to consider GHZ situation than the original Bell situation because it leads to sharper paradoxes, and there is a little bit less of hand waving involved. So we consider a GHZ situation in which we have 3 systems, 3 qubits, which are here in the GHZ state, and what is very important, this is a specific basis, okay? And they are sent to 3 labs in which inside of the lab is friend, in each of the labs is a friend and the local Wigner, okay? And the friends, they make the pre-measurements, and Wigners, they make measurements. And what is very interesting, that both do not variate their settings. Friends make pre-measurements in a fixed basis, and Wigners make measurements of system and friend, as Deutsch asked them, in a fixed something that I call effectively complementary basis. Okay, so just look that the complementary basis, they are still the standard for the qubits. Okay, in our case will be such. Okay, so if you remember this basis 1, and then of course there are two bases, which is I think everybody knows, and depending on this plus, we have outcomes plus minus. Okay, so friends pre-measure the qubits in basis 3, so this one. Friends inside, all of them pre-measure in this basis. Okay, and this means that if there is a system in this state, then they get correlated, and they end up in a system friend state, which is the most handy situation is to label it the same. Okay, but super Wigners measure this joint system in the second basis. Okay, with an I, without an I. Okay, and let us see what does it mean. Okay, so just look that. So recall that this is the situation that I described. So this is the measure correlation that is obtained in the friend's lab. Okay, so she gets correlated with the system, and now Wigner makes a measurement in a basis which is effectively complementary. So just look, here are the eigenstates of friend, okay, of friend's lab, of the measurement, and there is a unitary, trivial qubit unitary relation that relates the basis of measurement, let's say, or rather the final states of system plus friend, with the measurement, some of the elements of the measurement basis of Wigner. So this is the Wigner's measurement, and just look, this is the same unitary transformation. Now, if you have a GHG state and you put it into the third, in every local situation, you put it into the third basis, you will get something like that with some coefficient matrix. Okay, then just look that after, because there is this triviality here, after the interaction of friend with the system, of friends of the system, we have the same matrix here and such, and let's say a complete isomorphism. Okay, and look, so this is exactly like for qubits, and this unitary transformation is exactly like for qubits. And so if Wigner measures in this basis, that's a basis that will lead him to complementary results. And of course, this of course also means those identical unitary transformations that, let's say, the probabilities for certain results, whether we have Wigners or friends in such situations, they are just following the quantum predictions as we know them. And then, let's say, just look that both Wigners and friends, they measure in those bases, okay? And only phi is either 0 or pi over half, okay? And it's very easy. So that this defines basis 1 and basis 2. So the correlation function, which, as you know, this is the product of the results, which are plus minus 1 for each of them, is a cosinus of the sum of the phases, okay? And as I told you, phase 0 gives basis 2, phase pi over 2 gives 3. And for those specific bases, the correlation functions have GHZ EPR correlations. Okay, so for two friend settings, it's always, let's say, the correlation functions has the maximal value 1, but for only Wigner's settings, the correlation function has value -1. Okay, and then we perform the obvious thing. Okay, we write down the actual results by Wigner's as Wm. M is the number of the Wigner, they are plus minus 1, and the counterfactual outcomes by the virtual friends who are sitting in the lab, and they have these are those hallucinations, and those hallucinations must be in agreement with quantum mechanics. So the eigenvalues of the hallucinations are plus minus 1. Okay, and then if you look at those correlations then the results of the Wigners, they multiply to 1. And results of the Wigners and counterfactual results of friends, they have to multiply to -1. And if you do the trivial algebra, you see that it's not true that the counterfactual outcomes are imaginary, which is a nice thing to pronounce. Okay? So the conclusion is that the counterfactual outcomes of virtual friends form an internally inconsistent notion, and they do not exist even in theory. Perhaps I will skip the other things. Let's say the implications that we see, except let's say that Wigner's friend argument is Deutsch Wigner's argument is let's say doubtful. We kind of claim that we always, let's say, whenever it is needed, include decoherence, especially in sequential measurements. Okay? And also, we think that our result has some bearing on the, let's say, relational quantum mechanics, but about this we never wrote anything. And perhaps I will end with the founders. So thank you very much.
Thank you. Well, I'm afraid we are running out of time. I don't know if there is time for one short question, if anyone has. Czeslaw? But it has to be short.
It depends on an answer. I mean, hi, Marek.
Yes, hello.
So I fully agree with the technical part of your presentation of the second part. But you said, but I would like to understand more your interpretation. You said that the original Wigner argument is good, but the Deutsch one doesn't make sense. So can you go back to the slide where you introduced this original Wigner?
Yes. I hope if my system
the
allows.
answer is just yes or no then. I try to call.
Okay.
No. This, so I have more questions than this one. Can you go back to them? Okay, that's great. So I guess this before warning, they are all correct, I would say. I read your statement that the original Wigner is fine, that these 3 bullet points are all fine before the warning. So the friend does see one or the other answer, and Wigner's description of the seal lab is this entangled state.
Yes.
Now my question to you is, and I know that you think about the quantum states operationally as with respect to some measurements. What happens if the lab, as described in Wigner's description, is measured to confirm this state with the friend? What does friend see, feel, perceive? Before that,
So sorry,
you said that in this state, before the last measurement of Deutsch, which comes after the morning, the friend does see a well-defined outcome, and at the same time, Wigner's description of the seal lab is also fine. This also all belong to the original Wigner's friend, which you said it's fine.
Yes.
Now my question is, what do you think it happens to the friend or to his perception once the measurement is performed according to the Deutsch, namely confirming the state which was the Wigner's description? And I assume you allow this because otherwise the state will not have any meaning whatsoever.
No. So actually, I let's say perhaps I rushed too quickly, but simply at this moment, this result of the friend is erased. And so it is inaccessible.
I understand it's erased. Can you be more specific? What does it mean?
It's erased because just look, friend either sees plus minus or let's say, assume that friend does only the pre-measurement and this is the final description of what happened in the lab. Yes? Okay? I hope that you see my cursor. Or
yeah, we do.
Okay, so assume that this is the final description of the lab. Okay, and then Wigner performs a measurement on this lab, and this is a measurement that allows him also to confirm this superposition. Okay, then Wigner finds the friend in a superposition of seeing this and that.
So well, what is with the friend's perception? Does, in this moment of measurement, he still sees a definite outcome, or he has some experience outside of our everyday life?
No, that's why I called it hallucination, and I allowed it to be transitory. And I showed that even if it is transitory and it's a hallucination, even hallucination cannot exist. Okay, so let's say if we the basic thing that the basic message is that if we think that there is a definite result felt somehow by the friend, then such definite results give us a GHZ contradiction. But not in a GHZ experiment, but GHZ-like contradictions. That means that we can derive that plus minus 1 is equal to plus minus I. Okay?
Okay, I think Chatav is satisfied by the answer, so I'm afraid there is no more time for more answers. So thanks, Marek, for the talk, and we thank all the speakers of the session.
Thank you very much, and I miss you all.